Hey everybody, this is Larry. This is January 2nd, second day. Yay. Hope you're keeping up with your New Year's resolution. Hit the like button, hit the subscribe button, join me on Discord, ask me questions. Let's solve these problems together. You get to see me live, which includes the explanation, which means that sometimes I don't go to the solution right away. So feel free to fast forward or watch it in 2x or whatever. Anyway, today's problem is find a corresponding node of a binary tree in a clone of that tree. Okay, what does that even mean? That's a very long sentence, but okay. I mean, this is almost as long as the problem statement. Okay, and this given two binary trees. Okay, there's a target, and then clone what? Come again? Return a reference to the same node and note that is it a binary search tree? Note that you're not changing, and it must be a reference to node in the clone tree. Solve the problem to repeated values on the tree are allowed. Okay. It's a little bit awkward, but do we have to clone the tree? Given two binary trees, but I'm only seeing the input and it's only one node? Oh, huh. Okay. I mean, I'm just, so my initial confusion is that, you know, looking at the example inputs, yeah, looking at the example inputs, it's just not clear what the input should be. Like, where's the original, where's the clone? But so that's mostly my confusion a little bit. But otherwise, I think this is pretty straightforward. Well, okay, maybe not. There are a couple of I lied a little bit. There are a couple of strategies to do this. Like I said, if this is a binary search tree, then this is a little bit trivial, or maybe not trivial in the easy sense, but at least it's a textbook problem, right? And that is just finding a node in a binary search tree. The tricky part, even then, though, is about you know, if repeated values on a tree are allowed. So there are a couple of things you can do here. It is a binary tree, so then you can maybe take some advantage of that. There's some other things that I'm thinking about is just doing some kind of snapshot of the subtree, and you know, and there are different ways to do that in a snapshot kind of way. You know, you can, you know, obviously the expensive thing to do is just return the actual subtree and then compare it one by one. That's going to be n squared, which given that n is 10 to the 4th, that's going to be a little slow. Why is it n squared? Is because if you do an in-order traversal or any traversal, I guess post-order traversal is what you would do. Post-order traversal, and then you do an O of n comparison. That's going to be too slow. So the thing that I'm going to probably play around with is by basically something that's similar to Robin Carp, where we have a hash function and then we just play around with a hash function. I think that's what I'm going to do. And they might be probabilistically give me a wrong result, but we'll play around with that. And if that comes up, I mean, and of course, that with those kind of algorithms, it's going to always be a little tricky, but to like get it right exactly with respect to, like, you know, there are just false positives where, you know, you're gonna and maybe even false negatives are not possible, but false positive are possible with these kind of hashing things with collusion and stuff like that. And in an interview, you'll probably go over it as well. The values of the nodes of the tree are unique, but as we're talking about, we're going to upsolve it as if the repeated value in the trees are allowed. I don't think it matters that much, but yeah, okay. Yeah, so now it becomes two problems. One is, well, we have to find a target in the original, and then maybe generate some kind of I said snapshot or fingerprint or something like that, or hash, and then find that while we're generating cloned. And again, we're going to use the post-order traversal, so we're going to do that. We probably could do it in one recursive function, but for sake of understanding, and there's some things about it, so I'm going to do it in two functions together. So yeah, so let's have let's start with a search function, derp function, that allow us to search given a node and a target. We want to, what do we want to do, right? Well, we want to find, do we want to return a reference? Okay, yeah, let's do that. We want to return a reference to the node. So okay, so if node is none, we return none. So that would be our set no. Otherwise, we check whether if target is equal to node, and I think in this case, oh yeah, okay. So I just want to make sure that you can do this because, and the reason why we can do this is because if it's a node from the original tree, then the references should be the same. Otherwise, we might have to do something to make sure that they're the same, like dot value. But then, of course, in that case, you know, if the nodes of the tree are not unique, that's going to be an issue. So those are the things that I'm thinking about as I'm coding this. But in this case, it's okay, you know, that constraints there. So yeah, so then here, then we return. What do we want to do? Actually, we don't want to return the node because if we return the node, that's just the target. So I lied a little bit earlier. We actually want to return, say, a fingerprint of this node and the subtree, right? So actually, let me think about this. Maybe I'm wrong in this. Then now we don't actually have to do a search because this target is actually in the original tree node already. So we already have the reference to it, right? So we don't have to find it. So that was my bad. I was wrong on this one. So then we can just actually have a fingerprint of the subtree of the nodes, right? So I call it fingerprint. I mean, you could call it anything, right? So if node is none, let's just return 0, maybe. Yeah, okay. And then now we have to come up with a hash function, which is a little bit tricky. And let me think about what's a good hash function, right? I don't really, okay. Well, first of all, yeah, I'm just thinking through it a little bit what it means. But let's get a big prime for a mod. I usually just use whoops. I forgot that I'm in Python, so I could do something like this. This is a common big mod in a lot of problems, so that's what I'm going to use. But in general, especially if this one doesn't work out, I would honestly just Google for another big prime of like 10 digits or something like that. It's just to make sure that the collusions are not as frequent as you think it should be. And this is off the spot. I don't have a pre-made fingerprinting or hash function for this. So basically what I want is how do I want to combine this together, right? So we want, you know, no dot value. We want something that's a function of no dot value plus some, you know, plus some shift plus some function of no dot left dot value dot kind of recursively, right? So n plus obviously f of no dot right dot val. And in general, when you have a linear thing like a linked list or a string or something like that, you know, it's very natural, and it's not necessarily the best way, but at least it's functional, is to, you know, have something like no dot valued, you know, times some shift constant, and then no dot, not no dot value, right? Hash, something like that. Okay, hash is a keyword, but yeah. And then you add it to no dot value, and then so forth, right? But here, if we do that, then we're effectively just going to add the left value plus the right value. So right now I'm just thinking through a hash function that would work for this. And again, this is not prepared because otherwise this would be much faster, I suppose. I want to think about, so the way that I want to think about it is just drawing inspiration, and it might not be a perfect hash, to be honest, because we don't know the range of the numbers that are in the node. So we might have to play around with, you know, so this may have a bad case of false positives. But what I'm thinking of right now is the traditional formula of, okay, given that this node is, say, have an I, you can say left node is 2 times I plus 1, right node is 2 times I plus 2 or something like that, right? So that's a common formula that comes up, right? But then now we want, so what does this mean? So do we want this to be timesing the no dot right dot value, and this times no dot left dot value? I don't know that that's a great function, but but let's just mess around with this. I don't have any proofs for it, so yeah, so let's just play around, and if we get it wrong, then we'll have to play around some functions, right? So okay, so here now then hash is equal to, oops, Got that. Okay, so let's just call print. No, that's a terrible name. Variable naming is tough. So okay, so let's just call results. Is you go a result? Is you go to node dot value times, I don't know, some other prime that's like smaller than this, because I don't know the yeah, let's just, I don't know, like 1 2 4 2. No, that's not a prime. I don't know. I'm just googling if this is a prime. This is a random number. Okay, so it is not, because it is okay, 5-digit prime. That's basically okay. 99991 is okay, the largest, which is fine for me. I don't know. Like I said, I'm just trying new things, so we'll see. Yeah, and then we do something like result plus or equal to fingerprint node dot left, oops, and then result again. Okay, let me actually write it here so that when we if we have to change it, you know, we'll change it later. As I said, this is not gonna be perfect. It's just my way of doing it. Maybe there's an, you know, a smarter way of doing it as well. But I'm just playing around, and we'll see what happens. And then now that we're given this thing, we will mod it, and then we just return result. And then now we can return the fingerprint of oops, nope. So now we get, you know, target fingerprint is equal to fingerprint of target. And then now we could do a search find node based on that target, based on that hash, right? So fingerprint, target, fingerprint, maybe. Terrible names though, but as you know, it is what it is. Oh, and node, yes. And then here we can just use the same formula, because if you don't, then that you're gonna have not a good time. But key thing to note with this though is that we want to make sure that we don't do it in a way that is that makes it n square, right? So we do have to incorporate the fingerprinting into this. Otherwise, I mean, we could, if you're smart and there's a way to kind of you know, take advantage of memorization to make this into one function. But if this is already confusing enough for you, I just want to keep it simple, and that's why, which is that yeah, if node is none, we return 0. Otherwise, we have a current fingerprint is equal to search of node dot left. Oops. Wait. Let me do left fingerprint is equal to search dot left target fingerprint. Oops. How do I want to return this? This is a little bit awkward, but because usually I like I said on the streams, I try to avoid using global variables, but in this case it's a little bit yucky to do so. We can definitely do it, but I'm going to use a global just to kind of make it because I don't want to focus on that part yet. But yeah, okay. So then in that case, then we can just, you know, if we're using the target fingerprint, right fingerprint is equal to search node dot right, and then now, yeah, and then we have, you know, intermediate result is equal to node dot value times shift result left fingerprint result is equal, oh, huh, why did I do this twice? I meant, whoopsie daisies, I just meant this. Huh, would have to debug it. So, and there, like I said, there is some overlapping on how the code looks. Like I said, we can refactor it later if you like, but that's basically the reason. But yeah, but then now we have this result, and then if result is equal to target fingerprint, then we can update, you know, another thing. In either case, we want to return result. So then we have a global Oops, no, that's not how syntax works. Found node is equal to none. Found node is equal to node, right? And we have to do a non-local found node. And then at the very end, that's pretty much it. So we do a search from the root, and then we return found node. Oops. Let's give it a go. We'll see how that goes. Invalid syntax. Is that not the syntax for search node? Wait, what? Line 47. Oh, whoops. So while it's running, oh man, I wanted to copy and paste, but there's so many. Okay, root is not defined. Oh, it's called coned. Okay, I'm just so used to tree problems having a root. A lot of Leetcode problems. Okay, 7. Okay, fine. Is this good? This looks good, maybe. I don't know. It doesn't actually say. I guess it's unique, so it should be good. Let's see. That was 4, right? Yep. And this is 5. And again, you can choose any function here, and it would probably, any reasonable function that will probably work. But it's just that you may have more false positives depending on your constants, which I chose randomly, to be honest. Let's give it a go. Like I said, it's not a probabilistic algorithm, but there may be bad constants that give you the wrong answer. But yeah, so this is accepted. So what's the complexity of this one? Well, it is going to be linear time, because for every node on the coned tree, it takes, we just do a constant number of operations. So given n nodes, it's going to be O of n, right? We do a post-order traversal. And here too as well. I guess technically this is pre-order. I just kind of reordered it a different way. But yeah, in terms of space, well, this function and this function will take O of h because of the core stack, implicit core stack, and it's going to, depend on the height of the tree, that's how much the stack place will take. So it's going to be O of h, where h is at the worst case O of n. So linear time, linear space, worst case for this problem. Yeah, and I don't know. I actually didn't think that highly of this function, or at least, like I said, there are no false negatives because we have the same function on both sides, so they're always going to be true if the subtrees are true. It's just that it could also return true and the subtrees are not equal to each other. That's what we call a false positive, and that depends on your function finding. I am curious if there's a more traditional solution. So let's see if there's a solution. Let's go for it together. But yeah, this is going to be relatively optimal in either case. Because you have a tree, you're going to have to look through all of subtree anyway, so the space and the time should be roughly the same. Okay, let's look at solution. Oh, you could solve them in parallel once the target is... Okay, that actually is way more sensible than the way I did it. And you could do it that first search at the same time. I think that's okay. And by first search at the same time. I like my algorithm though. Recursive in order traversal. Wow, there's a lot of funky algorithms. I guess I did it in a unique way then. But yeah, Oh yeah, that's right. So the reason why I didn't. Okay. Yeah, I think, to be honest, looking back, maybe I should have done it this way. I think the reason why I didn't do it that way initially with the two in parallel recursion, and to be honest, I think I recommend that one a little bit better. But the reason why I didn't do it that way was because I just misread I misread the inputs. To be honest, I thought that the input was just a value, and if it is repeated, then I think I just didn't resolve that correctly. So that's my bad. I made the problem more complicated than it needs to be. Because, as if you kind of remember watching me doing it earlier, I did go, I was like, oh, yeah, actually, target is a reference on the original node. And if I had known that, then it would have been obvious. but when I found that out, I didn't go back and rethink my strategy, which I think you have to do from time to time. Otherwise, you get mentally stuck. It just happens that I have another algorithm that works. I don't know if I recommend this, to be honest. Now that looking back, I definitely recommend the other solution. So definitely play around with that. And for that solution is just basically because you know that the two trees are the same. You have a depth first search that move 2 nodes at a time. So it's going to look something like, and I only took a brief look, so I don't know, but yeah. So you do something like original, clone, target. You don't need all this stuff. You could actually just return this. Yeah, let's just do it globally for a quick hack. So this is equal to none, and then oops, I guess it should be before, just conventionally. So then you have dev search, original, clone, and target. Terrible names, but I don't want to shadow the variable names. And then basically, if O is equal to T, or let's just start with O is equal, if it's none, return. Otherwise, if O is equal to T, then none local found node. Found node is equal to C, which is the clone node, and then return. Otherwise, we just do a post order traversal, which is O.left, C.left, T, search O.right, C.right, T, right? And that's pretty much it, really, to be honest. So this one is actually way easier to explain. Let me make sure that I code it correctly first. But basically, I guess I made it a harder problem than it needs to be. But you just look at a pointer and a time. And because I think I got a little bit confused about whether the target was a value or a node, and whether that's a reference to the original node versus like just the value that are the same. I got a little bit mixed up. That's my bad. But yeah, this is also going to be linear time, linear space because of the core stack. And if you did breadth first search, it's the same, is that you need the space for the queue. So it's going to be linear time and linear space. And this is linear time, obviously, because you look at each node of the thing once, and and I could code it up in 2 minutes or whatever it is. So it probably is the easier way to go, because the other way, like I said, there is going to be false positives. So the input may not be, and there are ways to go around it, or at least make it more probabilistically unlikely. But yeah, that's all I have for this problem. I know that I did it a little bit weird and the long way, but I hope that maybe you learned something as well as a technique to do other things. I think the thing to notice is that there are often many other sometimes crazy ways to solve problems. Don't get stuck. Don't get don't always look for just the one solution. Always if you have different tools, you may solve the problems in different ways, and that's okay. But keep on learning, and just as I kind of forgot about this one. So yeah, that's all I have for this one. Happy New Year if you haven't seen a video this year yet or whatever, but do have a happy New Year, and hope y'all keep it up. Do it with me. I will see you tomorrow or whenever. Bye bye.